Good morning, ladies and gentlemen. Thank you for having me here. I am Zeni Rahmawati, or you can call me just Zeni. I'm from very far away here. I'm from Indonesia. Maybe if you have been there, you know how far is it. But if you haven't, I will give you some idea. So it's 21-hour flight, yeah? Yeah, so it's very a long travel for me, but it's okay. It's worth it because it's a very nice place, and I have been very welcomed in this university. Also, yesterday I was in IMP. Or maybe before I start my presentation, I can give you idea like where I come from. Okay. So basically my boss sent me this and asked me to present, so I just try to comply with him, yeah. So I'm from an institute called 10 November Institute of Technology. Yeah, it's a date, basically, the name. The date is like a historical things in my country. It's very important date, so we call it our institution with the 10 November Institute of Technology, and I'm from the chemistry department. Okay. Yeah, this is my campus. It looks green, but it's much hotter than here, yeah? It's about like 32 degrees in a normal situation, yeah? 30, 32. I think last week it's about 38. Yeah, so I think it's hotter than here, but more humid because we are surrounded by the sea, because we are islands, yeah? And I think we are much younger than you, yeah, than your university. Sorry, I think your university is like 1970 something, if I'm not mistaken. 74, yeah. I think we are about like 8 years after, yeah. And then this is my boss, and yeah, we are accredited like internationally by the German accreditation called ASEAN. And this is our colleague here, lecturers. We are from, mostly we are coming from, we did our PhD abroad, yeah. And we have some achievements, like this is like top 2% scientists in 2025. And we have 5 laboratories, 1 teaching laboratories, we call it fundamental laboratory, and we have fuel chemistry laboratory, and natural product and chemical synthesis. We have also microbial and instrumental, analytical, and also material chemistry and energy. So I belong to this group, which is the instrumental and analytical science laboratory, but I also collaborate with the fuel chemistry and energy laboratory here. Here is the head of the lab. We just skip that, yeah. You don't know them, and I don't think you're curious about that as well. So here is what we are working. Fusela is the fuel chemistry, which is related to what I'm working. It's about like fuel, renewable fuel, and etc. But then the renewable fuel and fossil fuel, we don't only work in 2 labs. We are working in like about 3 labs: the MCE, the Fusela, and the analytical chemistry as well. And here is our focus of the research. We have renewable energy and fossil fuel efficiency. This is what I'm working on. And also sustainable infrastructure. We have also advanced materials and environmental applications. This is our facility. I think you will have more fancy instrument than us. Yeah, just yeah. So basically, our department in Indonesia, our university is number 3. The first one is, I think, if I'm not mistaken, University of Indonesia, and ITB, or Institute of Technology of Bandung. So this is our achievement. We have the program like postdoc from inside, from Indonesia, also from abroad. Also, we have top tier research. We have national research collaboration and expertise research. So we have a lot of funding. And last year, our department is the best department in our institute. Yeah, please give applause to me and my department. Yeah. Okay, and this is our collaboration. In Australia, we have collaboration with Queensland and Curtin University. In UK, we have several. We have University of Aberdeen, where I did my PhD, Glasgow University, and also Manchester, Coventry, Cardiff, but we haven't mentioned here, and in several universities in Germany. In USA, we have Wisconsin and MIT, but I haven't mentioned that I have collaboration with IMP, so it's not written here yet. And in Asia, we have several collaboration as well. So basically, we have a lot of collaboration with our neighbors, yeah, from Malaysia, from Japan, China, Hong Kong, and etc. Okay, so if you want to collaborate with us, there are several schemes that we can do. For example, if you are students, then you can have like student exchange. We have students mobility, so we have a global engagement program. Then you can come to Indonesia and do some research over there, or do some like double degree. And also for the lecturer, we can have like visiting our researcher lecture. We have like, I can invite, for example, someone from here for like a week or a month. And of course, everything is on us. Yeah? And also joint research, like what I'm doing with IMP, and also joint publication and double degrees. Maybe that's just the brief idea where I come from. Okay, let's just, okay. Coming back to my presentation. Okay, so first of all, I thank you very much for Dr. Sandra for inviting me here, and thank you everybody for coming for this talk today. So in this very precious occasion, I would like to present one of my projects, which is the sustainable aviation fuel, or the production of green diesel to the oxygenation of natural oils and its derivatives. Actually, this is a project between my university, with University of Aberdeen, from UK, and University of Zeni, Malaysia, and Central Defense of Malaysian University. So for universities working this project, and this project also under the grant of the Ministry of Education. Okay, and the next maybe like 45 or 30 to 45 minutes, we will discuss about why we did this project and what is the method that we will use, and also what is the key funding, of course. First, why we did this project. So biofuel has been developed very long time in Indonesia. Our government has a project called like Indonesia blending mandates. It's basically we mix our fossil fuel with biofuel at certain proportion. For example, if we have a 2015 B10 and B15, it means we mix our fuel with 10% of biofuel and 90% of fossil fuel. We have success story from 2008 up to 2023. Of course, this success story makes our government become so ambitious. So in 2025, yeah, in 2025, they make like a more blending, like 40, but it's still going up at the moment, yeah, not reached yet until 2026. Of course, this is a very ambitious project. Every ambitious also have a challenge. What is the challenge? Our government, when we talk about biofuel, they rely on biodiesel. Yeah? But biodiesel has several drawbacks. Chemically speaking, it's actually like fatty acid methyl ester. It contains oxygen, so it has a lot of oxygen content. It cannot completely combust it, so it will create like a carbon deposition in the engine. And during the storage, it can be degraded. So there are a lot of issues with biodiesel. Why is that? Yeah, let's say again, if we look at the chemical structure here, biodiesel is actually fatty acid methyl ester with a long chain of carbon and the ester group here. So the idea of our project is we just cut off the ester group here to make green diesel, or we call it renewable hydrocarbon. Why? It doesn't have oxygen, of course, and also it's alkane, like the same as fossil fuel, like long chain alkane without the oxygen. And then, of course, because it's like a hydrocarbon and alkanes in a specific, it has more fuel properties better than biodiesel. For example, it has a higher Cetan number and other properties. No carbon deposition and higher calorific value. Okay, so when we want to make green diesel, what for? I mean, in the commercially, what for is the renewable hydrocarbon. So we try to make sustainable aviation fuel, or we call it SAF. In Indonesia, SAF is initiated in 2021, yeah, it's a bit late, yeah, by G2.5 project. So basically, we try to mix like aviation fuel from fossil fuel, like 97.5% with 2.5% SAF. And we tried on an aeroplane, flew from Jakarta to Bandung. And it was all right, like everything was okay. So it means we can develop SAF. That's why, of course, our government make another target, that short time target, like 1% blend by 2026 or this year. It means like commercially. Yeah? And then by 2060, we want to have like 50% blend between SAF and fossil fuel-based aviation. Of course, if we relate with SDGs, we try to contribute in these goals, affordable and clean energy, also the climate change. Okay. Okay, how we produce SAF? Sorry if it's so chemistry. I'm not sure if you are from chemistry department. I don't know where are you from. So I'm sorry if it's too chemistry. So how we produce SAF? If I can't, how to say, if I can't call it by myself, I mean like the term is not like based on theory or something like that. I normally call like the way we produce SAF can be in two ways. The first is like one step. One step, it means we straight away produce SAF from natural oils. How? Natural oil comprises of triglycerides, which is a very big molecule, and with one glycerol and 3 fatty acids attached. The fatty acid here can be saturated and unsaturated, like palmitic acids, stearic acid, oleic acid, linoleic, and etc. Every natural oils have about like 96 to 98% of triglyceride. Then we can straight away produce alkanes here, from here, by using like hydrogenation. First, we hydrogenate the triglyceride if there is unsaturated fatty acid here, for example, linoleic or oleic. And then we get fatty acid with the saturated chains. And then we crack them with hydrogen to produce free fatty acid and propane. And after that, the free fatty acid here can be converted to alkanes in 3 pathways. The first is hydrodeoxygenation, the second is decarbonylation and decarboxylation. In hydrodeoxygenation, we transform this fatty acid to be alkanes with the same chain as the fatty acid and water. In decarbonylation, we change this free fatty acid to alkanes with one less carbon atom and produce CO and H2O or water. So decarbonylation. And in decarboxylation, we don't need hydrogen. We produce alkane with one less carbon atom and CO2. We can make this, but you know, oil is complicated. Like sometimes we need some pre-treatment, especially if the oil is non-edible, because there are chemicals that will not make like our process become smoothly, and also we need a high requirement of hydrogen. So we can go with another route, which is I call 2 steps. So basically, we change or we transform this natural oil to biodiesel first, or fatty acid methyl ester, and then fatty acid methyl ester can be converted to alkanes by the hydrogenation, decarboxylation, decarbonylation, or decarboxylation, or in a very general term we call it deoxygenation. Okay, if we look at the reaction, it's like this. So the triglyceride, we react this with alcohol, normally methanol, and we produce fatty acid methyl ester. The reaction, we call it transesterification. We need base catalyst for that, and we need only mild temperature, like 50 to 80 degrees. That's why it's like very easy to conduct. Yeah. And then we need base catalysts like natrium hydroxide, calcium oxide, and etc. And then after we get the fatty acid methyl ester, we can convert this FAME or biodiesel to alkanes. For example, we can hydrogenate fatty acid methyl ester to aldehyde, and then alcohol, and further hydrogenation of alcohol can produce alkenes. We can also have decarboxylation and decarbonylation happen here, so we produce one less atom carbon alkanes. But then here we call it the deoxygenation reaction. So we need supported metal catalysts like platinum, palladium, ruthenium, cobalt, nickel, and then we need high pressure of hydrogen, like 10 bar to 100 bars, and the temperature is like about like 200 and up to 450. Okay, so that's the theory and the background behind my project, and now I want to explain how we did and then what is the result. First, we use palm oil biodiesel, so we don't use the oil like palm oil. We also don't use we didn't transform palm oil to biodiesel. We already have this biodiesel from commercial one. So the biodiesel from PT Wilmar, we use it at feedstock, and we check with GCMS, and we have these 3 methyl ester. The first is methyl myristate, which is very small proportion, and then methyl palmitate and methyl stearate. We don't want to jump straight away to the palm oil biodiesel, so we make this as a model first. We use methyl stearate. So we did the oxygenation of methyl stearate as a model compounds first before going with the biodiesel. Here we did the reaction, the deoxygenation in a batch reactor at temperature is 300 degrees and the pressure is 50 bar. And we define the result with the conversion and also alkane selectivity. The other reason why we also use methyl stearate is just not because of our feedstock, but almost every natural oil has like stearic acid. And every biodiesel from natural oil, of course, will have methyl stearate. Okay, here is the result. Yeah. First, if we look at the conversion, we tried with different reaction time from 30 minutes up to 14 hours. At first, at 30 minutes, we have a very low conversion, like below 20%. But of course, when we add the reaction time, we prolong the reaction time, we get like 87% conversion. If we look at the product, first we have a stearyl alcohol, the intermediates. At first, of course, it's very high conversion, yeah? But then when we prolong the reaction, it's getting lower up to like 20%. And the second product, it's the happy news for us. Why? This one, what we are looking for, the octadecane, because we want to have like long chain alkanes. So here, we have the first product that we want, which is the octadecane, and we see that the profile of selectivity is keep increasing up to like 56%. And then the second product also make us happy because we have heptadecane, so long chain alkanes as well. And then we see, even if it keep increasing, the selectivity is lower than the octadecane here. So we also want to know the pathway of the reactions. Is it decarboxylation, is it decarbonylation, or hydrodeoxygenation? So we learn further about the yield of our product. The first is the stearyl alcohol. At first it's low and then keep increasing after 2 hours. After like 6 hours, it's getting decreased. And if we look at the second profile of octadecane, then we see that it's related, because when it's getting decreased, it's suddenly getting increased like more than it should be. And if we look at this profile here, so we make assumption here that methyl stearate was converted to stearyl alcohol first, and this stearyl alcohol is further deoxygenated or hydrogenated to octadecane. And then if we look at the third product, which is the heptadecane, it's like doesn't bother with the second, the two products before. So we think that, oh, maybe it's not related with the stearyl alcohol, so maybe it's another route. So we propose that it comes from decarbonylation. So why we say that it's decarbonylation, because when we check the GCMS, there is like octadecanol in a trace amount. So octadecanol is there, but maybe because of the rate is very fast, so we didn't find octadecanol anymore. So then it's converted to heptadecane straight away. And to confirm about that, actually, before we did several reactions with the intermediates like stearyl alcohol, octadecanol, stearyl alcohol without hydrogen to check if the carboxylation happened, and etc. So we conclude that this reaction happened with the methyl stearate deoxygenation. So we are happy with this result. We have final product which is octadecane and heptadecane, but we still have intermediate stearyl alcohol. But of course, we are happy because this is what we are looking for, long chain alkanes. So then we move on to the palm oil biodiesel. But then, let me tell you something before I go further. The first reaction, we did it in University of Aberdeen with a fancy reactor. Yeah? And the second one, we did it in my university. So basically, it's a brand new project at the moment. And also we started to build we set our reactor, so we didn't have the same condition as we did the first one. So we still use batch reactor, but we cannot go the hydrogen pressure up to above 50 bar. So we compromise with higher temperature. And then we learn also with another catalyst, which is cobalt and nickel. But then today we don't talk about nickel, we just talk about cobalt. And also we learn about the influence of reaction time, metal loading or cobalt loading, and also catalyst mass. Okay, this is our catalyst, cobalt alumina, cobalt supported alumina, and also nickel supported on alumina. We use like wetness impregnation method. It's not fancy things. We just try to impregnate the cobalt nitrate. We use cobalt nitrate on the pore of alumina or on the surface of alumina, and we did drying. We calcine the catalyst and also reduce the catalyst. So we want to change from nitrate to oxide and then to metallic cobalt, because the metal one is the active site for this reaction. And then we characterize our sample with nitrogen adsorption desorption to check the porosity. We also use hydrogen TPR and SAM, of course, XRD. Here is the nitrogen adsorption desorption, or we check the porosity. We see here that this relates to the isotherm type 4, saying or indicating that the material is mesoporous with the loop hysteresis here. And then we can check here that when we add the cobalt loading from 2.5% up to 10%, we get decreasing surface area because of the deposition of active sites on the surface of support. And then we also did the X-ray diffraction or XRD. Of course, here we can see that we have the alumina, we have the cobalt oxide, we have also cobalt aluminate. So it's not great things because there's interaction between the active site and also the support to make a cobalt aluminate. So then we need the higher temperature and to reduce afterwards. So yeah, this is the X-ray. And then we check with SEM as well to check the morphology. And of course, we check the reducibility because we want to know like how much the cobalt oxide transformed to the cobalt metal, because that cobalt metal is the active site of our catalyst. And if we see here, we have actually three profiles, but it's overlap. Here is the transformation of CO3O4 to COO and then to CO metal or cobalt metal. And then for this one, it's like cobalt aluminate. We reduce cobalt aluminate here. So when we look at the reducibility of the catalyst, we see when we have higher cobalt loading, we have more reducibility. But there is no like 100%. So basically in our catalyst, there is still some oxide and some metal. So if we summarize the characteristic of the catalyst, we have the particle size is about like 7.2 nanometers, and also the surface area, it's keep decreasing, like I said before, because the deposition of the active site. On the support material is also the pore volume, same, and the reducibility keep increasing with the increase of cobalt loading. Okay, let's have a look to the product, like SAF production. Here, we can see that here is our product. Yeah, I cannot claim that this is SAF yet, because if we look at the selectivity, we know why. Okay, so at first we tried with the lowest loading, which is 2.5 cobalt on alumina, and we learned the influence of reaction times. Of course, when we prolong the reaction, we have like higher conversion up to like 70-something%. But then if we look at this here, 5% has higher conversion, but it's very black, very, how to say, the viscosity is too high. It's not like oil at all, or it's not like SAF at all. It's like, how to say, like lubricant. So we don't want to produce this anymore, so we skip the 5 hours for the next reactions. But then when we look at the selectivity, for 30 minutes and 1 hour, we haven't had any hydrocarbon that we were looking for, which is the alkanes. But surprisingly, we have alkenes. We don't know where it come from, because our reactant is methyl ester. And then if we did the hydrodeoxygenation, decarbonylation, we will not produce alkenes. But maybe hydroisomerization happens, cracking happens, because our support is alumina. Alumina has a acid site, like Bronsted acid site, and Lewis acid site as well, maybe. We haven't looked at this yet. And then after like 3 hours, we start making alkanes with a small selectivity. After 5 hours, we have a larger selectivity, but then we still like not happy with the appearance of the oil. So we say that, okay, 3 hours is the minimum reaction that we can produce alkanes, because if we look at before, this one, the oxygenate here means fatty alcohol, fatty aldehyde, like sterile alcohol, octadecanal, so it's basically, it's still intermediates, not the alkanes yet. Okay, and then afterwards, we check the influence of cobalt loading. Of course, we have like 0, it means we only use alumina without cobalt at all, and we have a very low conversion, like 10%. And then as we increase the cobalt loading 2.5 to 10%, of course, it's getting increased. And then if we look at the profile of the alkanes, this is the alkanes. But we still have like question, why alkene is always there? Yeah. Okay, so here is the appearance of the product. Yeah, here is the biodiesel, and this one we can see here like from the alumina only, with a small conversion, it's like a bit like darker, but then it's getting darker and darker like after 2.5%. Okay. Okay, and then we check. So here, what happened is like, even if we add the cobalt loading, we still have small amount of alkenes, so we are not happy. So what happened? Why we don't get like a lot of alkenes like what we did with the methyl stearate, like up to like 50% something, the selectivity of octadecane, and if we add with the heptadecane, it will be like above like 70 something. But here we have like a very small, even when we learn about the reaction time, we change the cobalt loading, it's still very low. So we try to add the mass of the catalyst. When we add the mass of the catalyst, oh sorry, we didn't include the 2%, it's up to 1% mass of the catalyst, yeah, compared to the biodiesel, the reactant, we see we have a lot of alkanes, selectivity increased here, and then the conversion also increased with the increase of the catalyst mass, of course, but then 0.4% we have higher selectivity of alkanes, but they are not too much different. So we are happy. It means that afterwards we need to check out like the mass of the catalyst as well. So yeah, after getting alkanes, finally, yeah, we check the stability of the catalyst. We reuse the catalyst like 3 times straight away without doing anything. Like we didn't treat anything. Like after the catalyst, after the reaction done, we use straight away the catalyst, the used catalyst to the next reaction, to the next cycle. And we see here the second one, the conversion decreased from 62 to like 53. And then the third one is getting decreased up to like 50%. It's very significant. Then we tried, so we see like it's not that stable, and it's only like 3 times, but we already have a very low conversion. So what we did is we regenerate the catalyst by calcination and reduction, the same what we did with when we prepare our catalyst. And then we got much better, but we haven't reached the previous one. It's like double from the third usage here, but it's still very low compared to the first one, like a half. So we have to think about like how we regenerate our catalyst to make like a better result from the reuse here. Okay, this one is what we propose from the result, the reaction pathway. So we have fatty acid methyl ester here, which is like methyl stearate, palmitate, and myristate. And from that, we convert this biodiesel or methyl ester to fatty acid. And then from fatty acid, we change or convert this to even chain hydrocarbon. And then this fatty acid, it's also can be transformed to aldehyde. And this aldehyde can be transformed to out-chain hydrocarbon with decarbonylation or straight away decarboxylation. And we have a short chain alkenes in our result as well, so maybe cracking happen over there, but we haven't checked the cracking one here. So that's all what I can present today. So it means like, even though it's not that great, the result, we can see that, okay, that we can transform the biodiesel from palm oil to SAF using cobalt catalyst. But then if we look at the selectivity, if we look at the selectivity of the alkane, it's still a bit challenging to us. It's not great, the result. And if we look at the stability, we also need to think about another method to regenerate our catalyst. So yeah, because of the result, we are not doing this project anymore. Yeah, we are moving to non-edible oil. Why? Because palm oil is edible, so we don't want to have like constraint between food and energy. So now we are working in a non-edible project, which is, for example, I'm not sure if you have this here. We have in Indonesia called Tatsambi oil and Calophyllum inoculum oil. So we have this oil as a feedstock, and this one that we are working with IMP, with Dr. Heriberto. We have a grant from my university and from Ministry of Finance. And also the other two, we have also the grants from the research agency in Indonesia. Okay, that's all that I can present today. Thank you. I thank you very much for my colleague and for my collaborator from this university, Aberdeen, and University Sains Malaysia, and Central Defense Malaysian University, and this grant, this body that gave me the grants, and also Dr. Heriberto and Dr. Sandra for inviting me, and also thank you everybody for listening. Thank you very much.
Gracias por su presentación. Thank you for your presentation. We have a little bit time for questions. Preguntas. Go ahead.
Oh, I see. Okay. Can I use this or not? I mean, my voice is already so. Okay. So actually, if we look at the catalyst, I haven't mentioned before, we have the activation. Yeah, the deactivation happened in, so we check first leaching, if the active site is leaching, something like that, but it's not. It's like leach a very little bit. For example, if the first loading is like 4%, and then after we use for the reaction, we check, it's about like 3.9 or something. So leaching is not the problem. And then we also check, the carbon deposition. So that's the poisoning happened because there's like a lot of carbon deposition. So we check the fresh catalyst with the used one, and we figure out that there are several intermediates that is still strongly attached on the surface of our catalyst, like alcohol and aldehyde. So the oxygenates basically, and also with the long chains, the same as the with the reactant. So we conclude that okay, the poisoning. That's why the stability is saying that it's keep decreasing because of the poisoning. So and not because of the poisoning, because of the deactivation. But the type of deactivation is not poisoning, but carbon deposition. Yeah, if we look at the poisoning, we don't have something like sulfur or something like substance that will poison our catalyst. And we also check sintering as well. Yeah, but it didn't happen, I think, if I'm not mistaken. Yeah, yeah. We have to check like the particle size from the first one to the used one. But then we conclude that the carbon deposition is the thing that really, I mean, the main problem of the decrease or the low stability of our catalyst. Yeah.
Okay.
Thank you very much for your presentation. Mm-hmm. I have several questions, but I would.
It's okay.
Could you talk about the economy of the process that you are working? Because I think it's a very important issue about that, yeah? So, because green diesel, you start from green diesel to, for biodiesel to produce SAF, yeah? So I don't know how will be the cost of the product at the end.
Okay, yeah. Is this the first question? Let me just answer, yeah. Okay, the main challenge of green diesel or SAF in general is the price. Why? Because the feedstock is expensive compared to the fossil fuel one, honestly speaking. Because natural oil is a bit expensive, yeah, compared to if we calculate like economically. And also the other thing is like the source of hydrogen. The source of hydrogen is expensive as well. It's not only expensive, it's not renewable. The one that we are using is just commercial hydrogen. We haven't thought about like the sustainable hydrogen or renewable hydrogen production. So if we compare to the fossil fuel one, we are still much more expensive than that. But if we compare between the biodiesel and green diesel, yeah, in the process, biodiesel is of course much simpler and also need less energy, more or cheaper. But then if we compare like one step or two steps, for example, if we straight away produce SAF from oil, then it will be more expensive than we produce SAF from oil, we convert to biodiesel and then to SAF. Yeah, so it's still much cheaper, but if we compare to the fossil fuel one, it's still more expensive. That's why, that's the big, it's a big homework for SAF production. That's why we are trying to look for something that is much cheaper, like for example, non-edible oil. But non-edible oil also has his own drawbacks, because the availability, we cannot suddenly ask everybody to grow this certain type of plant, because we want to make this as a feedstock for fossil fuel, for aviation fuel. And the second is because non-edible oil always has something that is something that we need to remove before using a feedstock. For example, it's like this, it contains like gum, something like that, or it comprises of toxic material, toxic chemicals that we need to get rid of, or pre-treatment before that, yeah. Okay.
I have another question regarding the catalyst. You talk about cobalt, the world also over nickel. From where you bring the vessel sold?
Okay. Well, okay, I will show you something then. Perhaps. Okay. Okay. Yeah. So, yeah, basically, actually, we did with we tried with several catalysts, not only cobalt and nickel. We tried ruthenium as well, but it's super, super expensive, yeah. So, yeah, basically, when I did my research before in Aberdeen, we have a research group, which is catalysis, but with energy, like some people working for Fischer-Tropsch, hydrocracking, me, biofuel, and the other things over there. Sometimes we share each other our catalysts just to test. For example, okay, I have like cobalt, nickel, and my friend try, okay, it's not good. And so I checked with ruthenium, it's too expensive. We didn't continue about that. But then if we look at the catalyst, here is what I have done and what I search in literature. Yeah, it depends. The result is depends. Really depends on what? Depends on which one we want to get. It's the selectivity or the conversion. And the conversion is like in general. Selectivity is the most important here that we talk about, because if we use, for example, cobalt is very good for both hydrodeoxygenation or decarboxylation or decarbonylation. We can get even number of hydrocarbon or odd number of hydrocarbon. So if we want to go for HDO or decarbonylation, we just change the temperature and the pressure. But if nickel is very good in decarboxylation and decarbonylation. So we tend to get C17, C15, yeah, and etc. The other odd one. So if we want to get the C number which is odd, so we go with nickel. If we want to have like more to the HDO or the even number, we go with cobalt. But then cobalt and nickel, basically, I can say from my experience at the same level, the only problem is like the deactivation. Cobalt is very easy to deactivate. And the other thing is like the superior of nickel is like nickel, when it's in metallic state, it's not easy to reoxidize. But cobalt, when we have metallic cobalt and we put it on the air, it's like in several seconds, it reoxidizes. So after we reduce our catalyst, we have to straight away use it for the oxygenation reaction. If not, then it will not be in a metallic cobalt anymore, or maybe the metallic cobalt will be decreased. So there is a plus and minus between cobalt and nickel. We just need to figure out what we want more, like stability or selectivity, something like that.
The question was because we were working nickel aluminum,
Yeah.
starting from a layer double hydroxide.
Mm-hmm.
That worked very well, but we don't need to reduce all the nickel. We need nickel oxide, and the vacancies that you are creating during that treatment are very good for selectivity. I don't know if you tried that.
Yeah, I tried with nickel as well. I think I didn't mention here, like, I did like complete reaction the same as cobalt with nickel as well. Yeah, I think in terms of stability, nickel is better than cobalt. Yeah. If I'm not mistaken, I haven't showed the slide. And I think the result is also, if we look at the conversion, is also much better. Yeah. But the alkanes, again, it's with the old one. Yeah. You are welcome.
¿Otra pregunta de alguien más? Anímense, adelante.
Why is it the government supporting this initiative if it is not economically good?
Sorry?
Why is it the government supporting these initiatives if they are not economically good enough?
Okay. Well, do you want the real answer or political answer? Okay. Well, how to say? Let me have a drink. Yeah. I will talk something very important. Please, don't say anything. Yeah. Please, after we finish this talk, nobody talks anything. Yeah.
It's recorded. The political.
Okay, so palm oil. The first oil that we try is palm oil. Why? Indonesia is the biggest producer of palm oil in the world. Yeah, and then so palm oil is available. Like availability is like very high. It's already commercial. It's ready to be applied as a feedstock. And then there are some successful stories when we use palm oil. Because of the availability, because of the characteristic of the palm oil as well. And we have a lot in our country. So it's easy way. For example, it's just in a simple term, it's like easy way to use the already available and with the good properties as well. But then in another way, we have follow as well we have to follow the agreement, the Paris Agreement, and etc. The blending mandate. So we have to abide this one. So we have to rush to make like more biofuel or SAF, and then the palm oil is easy choice. But then after that, we see that the problem here it's expensive and it's food, and also the palm oil plantations. There is a problem like last year, like 2025. There's a very huge flood in one of our island because of the illegal plantation of palm oil. So we are shifting to non-edible one. But then, of course, we have to I don't know, like how to make it like simple, because non-edible, we have a lot of non-edible oils in Indonesia, but the availability is not like palm oil that is already there commercially, and there is like a ready plantation, something like that. So maybe this transition also needs some time, but then we have a target for that. Yeah, let my government think about it. I will just do the research on it, yeah. Yeah, thank you. You're welcome.
¿Alguien más? ¿Alguna otra pregunta? ¿Sí? ¿Hay otras? ¿Ah, no? Siempre no. Okay, thank you very much.
You're welcome.
I give you a certificate.
I can say that. Oh, where is it? Oh, it's right there.
I give you this. Es una constancia por la participación. It's a certificate also in English. And I give you aguamito.
Oh, that's so cute.
Thank you very much. Thank you very much.
Oh, can we take picture?
Yeah.
Maybe can somebody help me with this?
Al revés, ¿no?
This? Maybe. You're so cute. Okay.
Necesitaríamos tomarlas al revés para que se vean todos.
También.
¿Sí? Maybe the other way. To see all of them.
Okay.
Sonríen, ¿eh?
Oh, I see.
Sí. Sonrían. Hagan tu cara linda. Venga, para la derecha.
Ok, a las 3, 2, 1. 3, 2,
Se nos canta la
1,
sonrisa.
listo.